this video, I will be examining various E2 reactions. The purpose of this is to review the things that you have already seen. So this corresponds to the Chem Activity 11 Addendum 2. And I'm starting with the classic example of having a strong base. I also acknowledge that it is a strong nucleophile, but we're only focusing on E2 reactions here. Recall that the requirement for an E2 reaction is that the leaving group must be antiperiplanar to the beta hydrogen. Recall also that E2 reactions will generally go with a small, strong base, Zaitsev. So the regiochemistry here will be Zaitsev. In looking at my substrate, I see that I have some beta hydrogens here and beta hydrogens here. It will be the beta hydrogens on the left that get removed to form the more substituted product. That will be the Zaitsev product. Note that I have two beta hydrogens. Therefore, there are two ways that those beta hydrogens can be antiperiplanar. This will give rise to two different products. And so in this case, I'm not so much emphasizing the mechanism, but rather thinking about the products. So in one case, I'll have the carbon-to-carbon double bond in the middle part of the structure, starting on carbon number 2, and I'll have this trans, or E, configuration. Another possibility for a Zaitsev elimination is to have the Z configuration. As we know, the trans will be preferred. So the trans is the major product, and therefore this is an example of stereoselectivity. So let me just write this down here, stereoselectivity, and then we can say that in this case the stereoselectivity favors the trans or the E. So these reactions have both regioselectivity as well as stereoselectivity. In the next case, you can see that I'm using the same substrate, but now I have a strong base. But what's characteristic about this strong base is that it's big and bulky. Being big and bulky means that instead of favoring the Zaitsev product, we will favor or have a regioselectivity of the Hofmann product. This is a kinetic effect and applies to E2 reactions because the big, strong, bulky base is involved in that one and only step. So we have beta hydrogens here and we have beta hydrogens here. The hydrogens that will be more quickly removed because they can be accessed more readily will be the beta hydrogens on the right. As a result, this product will form. And we'll see the carbon-to-carbon double bond is on the end. In this case, there is no stereoselectivity that we need to worry about in the sense that this product doesn't have a stereoisomer. That said, stereoselectivity can still play a role, and we would expect the trans or the E configuration to be the major product. In my next example, I'm trying to emphasize something else. So here you can see that once again I have a strong base that is small. This sets us up for the regiochemistry or regioselectivity of being Zaitsev. I know therefore that it will be this beta hydrogen that will be removed. It is important that that hydrogen adopt an antiperiplanar orientation. As such, only one particular stereoisomer will form. My preference is to redraw the structure so that I can see that that beta hydrogen is antiperiplanar. I also prefer using the wedge and dash rather than the Newman projections. So to do this, I'm going to draw this bond in the plane. I have my leaving group into the plane. My hydrogen's going away. There's my methyl group. And I'm going to allow rotation about the carbon-to-carbon bond between the alpha carbon and the beta carbon. In so doing, I will put the beta hydrogen into the plane. I will have a CH2, CH3 going back, and a methyl group coming out. Now I can see that my beta hydrogen is 180 degrees from the bromine in the same plane. When I think about what sort of product will form then, I can see that, for instance, the two methyl groups are on the same side. So I'm just highlighting that. Therefore, in my product, I'm going to expect to have the two methyl groups on the same side. There's the hydrogen on the opposite side, and I have a CH2CH3 on the opposite side. We would say that this reaction is both stereoselective and stereospecific. Let me write this down. It is stereoselective because one particular stereoisomer is formed over the other stereoisomer. And in this particular case, you can see that the stereoisomer that is formed preferentially is our E stereoisomer. It's also stereospecific because I'm starting with one particular stereoisomer, and that results in forming another particular stereoisomer. Recall that stereospecificity is one aspect or a subset of stereoselective reactions. To emphasize the idea that this reaction is stereospecific, if we briefly consider the other stereoisomer reactant or substrate. So for instance, I'm now going to draw this, let's say in green, and that would be this particular stereoisomer. So there's my leaving group, here's my hydrogen, methyl group, there's the hydrogen in the plane, and now we'll have the CH2CH3 coming out at us, and the methyl group going back. So I've switched two different groups. That is now the stereoisomer. If we consider the product that would form as a result of an E2 reaction for this particular substrate, we would see that the hydrogen would be on that side, methyl group here, and a CH2CH3 on the same side as the methyl group, and the other methyl on the opposite side of the first methyl group. In this particular case, we have therefore the Z stereoisomer that would form. Again, these reactions are stereospecific. We first introduced the E2 reactions, focusing our attention on alkyl halides that involve chains. But then we turned our attention to ring structures. There is also the requirement that in an E2 reaction that the beta hydrogen be antiperiplanar to the leaving group. This can result in some interesting outcomes. So if we take a look at my first example, I see that in fact I have two beta hydrogens right here. There's a beta hydrogen, and here's another beta hydrogen that are on opposite sides of the leaving group. I know that in a certain chair conformation, those beta hydrogens can be antiperiplanar to the leaving group. Notice also I have a small, strong base. Therefore, I would expect that if anything, this reaction would go Zaitsev. So therefore, I would expect the beta hydrogen on the left to be the one that would be removed. And fortunately, it can be removed because it would be in a certain chair conformation 180 degrees from the leaving group. Here is that chair conformation I'm talking about. There's the beta hydrogen that can be removed. Here is the leaving group. Therefore, the product that I would expect to form, and I'm going to draw it not in the chair arrangement, but rather like this, especially because we're forming a double bond. Here is that isopropyl group, and then I'd expect the double bond to be right there. We would say that this product has a regiochemistry of Zaitsev. Although there is a requirement for the beta hydrogen to be antiperiplanar to the leaving group in this reaction, we don't usually talk about the stereochemistry because actually we're kind of limited in a sense to what sort of stereoisomer that would form when we're working with these very small rings, that is rings of 8 carbons and less. So essentially the stereochemistry is less important, but certainly the regiochemistry is important. If we look at our next example, we have the same small strong base. We have a beta hydrogen here, and we have, of course, beta hydrogens on the other side. The beta hydrogens on the other side, on the right-hand side, do have or include a beta hydrogen that is 180 degrees from the leaving group in an antiperiplanar arrangement. However, the beta hydrogen that's on the left-hand side, you can see is on the same side as the leaving group. It would be impossible to consider a chair conformation where that beta hydrogen could be 180 degrees away from the leaving group. Therefore, although we have a small strong base, it will not be possible for the regiochemistry to be Zaitsev. Rather, the regiochemistry by default will have to be Hofmann, because it'll be that beta hydrogen, the one that I just circled, that will be removed. We can see this more clearly in the chair conformation. Here's the beta hydrogen on the left-hand side that would result in the Zaitsev product. You can see that it does not have an antiperiplanar arrangement. Even if we were to draw the other chair conformation, it still would not have an antiperiplanar arrangement. However, this hydrogen, which is on the opposite side of the ring, is antiperiplanar to that bromine. Therefore, the product that we would expect to result would be this Hofmann product. So sometimes the Hofmann product will be arrived at on a ring structure even if we're using a small, strong base. So watch for this when you're working with rings and look for whether or not the beta hydrogen is in fact on the opposite side of the ring structure. As I've mentioned in class, I don't think it's important that you actually draw the chair, but look for this beta hydrogen being on the opposite side of the leaving group. I hope that you have found this brief review of the E2 reactions to be helpful in seeing all these different possibilities on one page.